Yeah? That is a security assessment of the Internet Protocol version 6. So here I will be presenting an overview of this project and a brief discussion about some of the security implications of IPv6. So this is the agenda for this presentation. I will start with an overview of this project that I'm carrying out on behalf of CPNI. I will provide a brief comparison between IPv4 and IPv6 so that if anybody is not really into IPv6, you may understand the rest of the presentation. I will provide an introduction on IPv6 addressing, a discussion of fragmentation and reassembly, together with the security, a discussion of the security implications. We will go through the ICMP version 6 protocol, how it is used for address resolution and stateless auto-configuration. Then I will provide some thoughts on IPv6 security, and then we will have some time for questions and hopefully answers. So during the last couple of years, as I was saying, I have been working on security assessment on IPv6 for the UK CPNI. This is the same type of project, the same sort of project that I had been working on before, but on TCP and IPv4. I think it was last year that I had presented, I had made a presentation on the security implications of TCP and IPv4. We published these two documents in the last couple of years. So this is the same sort of project. The project is about, first of all, performing a security assessment of the specifications themselves. So we are going through all the relevant specifications and trying to find ways in which they could be exploited. Then we also try to perform a security assessment of common implementation strategies, which means that sometimes the actual implementations don't follow the specifications, or sometimes the specifications are open to different behaviors. So we also try to analyze what real implementations are doing. When we find potential issues, potential security issues, we try to produce security assessment tools. The idea is to try and practice whether those issues, whether those vulnerabilities actually exist or not. And finally, the final result of the project is going to be a paper or a technical report, if you want to call it, similar to the one that we had already published on TCP and IPv4, but it's much bigger, right? So far, I think we are in 160 pages or something, and we are sort of halfway there. During this time, we have been cooperating with vendors. Whenever we find potential issues in the specifications or in some implementations, we contact vendors. If we have tools, we send vendors those tools. And the idea is that if they have the problem, they have that problem in their implementations, that they can fix it before our document gets published. But also because we think that in order to produce best practices, it's interesting to get feedback from the people working on the actual code. So that of producing this best practices document, it's a process in which we write some recommendations, get feedback from vendors, and the document improves in the meantime. Just to give you an idea, when we work on the TCP and IPv4 documents, I think we had something like a 2-year period in which we were getting feedback from vendors and updating the document and so on. If anybody here is actually working on IPv6 code, I'd like to hear from you. At the end of the presentation, you will have my contact details. And it would be interesting to get in touch with you so that we may discuss some of the stuff that we cannot actually publicly release right now, but we can discuss with a limited number of people. So let's start with a brief comparison between IPv4 and IPv6. Despite the broad claims about IPv6, the differences between IPv6 and IPv4 are not that many. Here I am providing like a very small summary of some of the characteristics between IPv4 and IPv6. First one is about addressing. Probably addressing, that of having a larger address space is the only motivation for IPv6, even when there are claims for improved security, improved quality of service, auto-configuration, and so on. In my opinion, the real only motivation for IPv6 is the larger address space, and that's it. So then one of the biggest differences, if you want, is that in IPv4 the addresses are 32 bits, whereas in IPv6 they are 128 bits. When it comes to auto-configuration, in IPv4, real systems use DHCP, although there was in IPv4 support for router solicitations and router advertisements. They have not been widely implemented, but they do exist for IPv4. In IPv6, what's mandatory is the support for router solicitations and router advertisements. That's what is usually called stateless auto-configuration. And then while there exists version 6 of DHCP, its support is optional. Address resolution in IPv4 is performed with the address resolution protocol that runs directly over the layer 2 protocol, for example, Ethernet, whereas in IPv6, address resolution is performed with the Internet Control Message Protocol version 6. So this is one of the reasons for which in IPv6 you actually depend on ICMP, whereas in IPv4, for most of the part, you can actually filter it without any interoperability implications. When it comes to IPsec, the support in IPv4 is optional, whereas in IPv6 it's supposed to be mandatory. I don't know if I have a slide about this, but if not, I will provide some discussion about this mandatoriness of IPsec in IPv6. And finally, when it comes to fragmentation, in IPv4 it's performed both in hosts and in routers, whereas in IPv6 it's performed only in the end host, end systems. Here is a comparison of the header format of both IPv4 and IPv6. The IPv4 header is on top. The IPv6 header is on bottom. I'm not sure if it's clear from the IPv4 header, but there are some of the header fields that are not printed in such a strong font. Those are the header fields that have sort of been removed from the IPv6 header. For example, you don't have an identification field, a flags field, or a fragment offset field, or a checksum. So this is the IPv6 header field, where you have a version field similar to the one in IPv4, traffic class, that is the same sort of thing as the IPv4 type of service, payload length, same thing as the total length. Next header is the protocol field in IPv4, a hop limit, that is the time to live in IPv4, and then you have the source and destination addresses. Basically, some of the fields that were mandatory in the IPv4 header have been moved out. It's not really that they have been removed from the protocol, but actually, if you really need those fields, they are added with extension headers. They are not mandatory in the fixed IPv6 header. IPv6 addressing. IPv6 basically supports 3 types of addresses: unicast, multicast, and anycast. Actually, the same type of addresses are supported in IPv4. Unicast addresses, of course, identify a single interface, and when a packet is sent to a unicast address, it's delivered just to a single interface. Multicast addresses identify a set of interfaces, and if you send a packet to a multicast address, it's delivered to many systems. And finally, anycast addresses identify a set of systems, but if you send a packet to an anycast address, it's received by only one of those systems, okay? For the most part, the difference between anycast addresses and unicast is just a routing artifact, because it's not that the addresses are different, just that from the routing infrastructure, the packets, in the case of anycast, are routed to the nearest system, whereas in the case of unicast, they are supposed to get only to a single place. And also another characteristic of IPv6 addressing is that it has what they call a scoped address architecture. That means that for every of these types of addresses, you have addresses of different scope. Probably the most trivial example is linked local addresses that, as you may expect, are addresses that are supposed to be valid only on a specific link. And on the other hand, for example, you have global addresses that are the addresses that you are supposed to access from any place in the internet and are supposed to be routable over the whole internet. They did have what they used to call site local addresses, but those addresses were deprecated. Okay. So here we have the format of global unicast addresses. These are the only ones that I will be sort of discussing because are the most interesting, if you want, from a security point of view. Basically, you have a global routing prefix. This is sort of similar to IPv4 addresses. Then you have a subnet ID. And finally, you have the interface ID. If you are using stateless auto-configuration, which is a mechanism that I will be discussing in the next few slides, the interface ID is usually a 64 field that is selected from the MAC address in the event that you are running Ethernet. Okay. So an interesting point to make about IPv6 global addresses is that there's usually this myth that with IPv6 it's very difficult to perform a brute force scan because as the address space is so large, it's actually very difficult for an attacker to find a live host. So while I was analyzing this, I tried to find out if there were any patterns in which real networks were assigning the IP addresses. Okay, the IPv6 address space, of course, is larger, but the point here was how it was actually being used. So for quite some time, I was looking for real-world data, and I ended up finding this paper by David Malone. He did a study on how IPv6 addresses are assigned, and to get you like a rough picture of the results that he got is that for host, 50% of the addresses are the result of auto-configuration, which means that, of course, you have that global routing prefix, the subnet ID, and then you have the interface ID. 20% of the addresses are IPv4 based, which means that the interface ID part is not actually selected from the MAC address, but actually it's an IPv4, it's like an embedded IPv4 address. That's probably because in some cases the administrators find it easier to be able to assign very similar addresses to the same interface. So rather than having a completely different address, a completely different IPv6 address from the IPv4 address that interface had, they sort of embed the IPv4 address in the IPv6 address. 10% of the addresses were Teredo addresses. Teredo is a transition mechanism that was proposed by Microsoft. And then an 8% of the addresses were what this paper calls low byte addresses, which means that the whole interface ID is zeros, but just the less significant byte is selected from 1, 2, 3, 4, 5, and so on. Okay? Then these numbers are for host, which means, of course, end systems. And then David Malone did the same study, but for infrastructure, that means routers. And he found that 70% of the addresses were low byte addresses, which means that for the most part, the addresses of these systems are manually selected, and the whole interface ID is all zeros except for the less significant byte that starts from 1 and is increased from there. And then 5% of those addresses were IPv4 based, which means again that an IPv4 address is embedded in the interface ID of the IPv6 address. So from these numbers, one might get an idea, or one might get to the conclusion that it's not actually true that it's unfeasible to perform a brute force scan of an IPv6 network, because while it's true that the IPv6 address space is much larger, the way in which real systems or real administrators usually assign those addresses do follow a pattern. And even if you think, for example, about the 50% of auto-configure addresses there, it's not that you have like a completely random interface ID, because one could imagine, for example, that if some company purchases, I don't know, 200 Ethernet cards, chances are that the MAC addresses are going to be consecutive, because after all, MAC addresses are kind of like a serial number. They have 3 bytes that correspond to the vendor and 3 other bytes that are selected by the vendor. So even in those cases, if an attacker were able to find an alive host in that network, then chances are that he should be able to find the rest of the systems that belong to that network. And another consideration to make here is that even if this wasn't true, I mean, even if the addresses were assigned in kind of like a random way, one should consider that nowadays there is a very, very large number of hosts that are owned. For example, think about the number of hosts that a typical botnet has. And this means that it's very simple for an attacker to get access to an end system, and once that he gets access to that end system, he has many other means, many other ways to actually find all the systems that belong to that subnet. Think about, for example, sniffing the network, using all the multicast addresses that IPv6 provides, using ICMP echo requests and responses, and so on. So from my perspective, while we need some more data, other than the one that David got or published in this paper, my take is that the claim that brute force scanning of IPv6 networks is completely unfeasible, well, it's not actually true, but it's more a myth than anything else. So let's jump to fragmentation and reassembly. As I was mentioning in one of the first few slides, IPv6 removes the relevant fields for fragmentation, like the more fragment bits, the identification field, and so on. And basically, they take all those fields out of the mandatory field and provide a fragmentation header that basically, when you add that fragmentation header to the fixed IPv6 header, you get back all those fields, okay? So here's the format of the fragmentation header. Basically, it has a next header field that just identifies the next extension header or the upper layer protocol, a couple of reserved fields, a fragment offset, which of course is similar to the fragment offset that you had in IPv4, a more fragments bit, same thing as in IPv4, and finally an identification field which works in exactly the same way as the IPv4 counterpart, except for the fact that it's 32 bits compared to the 16-bit long field that you had in IPv4. So let's talk a bit about the security implications of IPv6 fragmentation. Probably one of the most important ones is the same thing as for IPv4. Fragmentation is a stateful operation for a stateless protocol. IPv4 is supposed to be stateless, but when you add fragmentation to it, that means that a system that receives a fragment needs to wait for the other fragments to arrive. That means that the system needs to allocate memory for those fragments. And of course, if an attacker were to forge a large number of fragments and send it to that node, well, that victim system could, of course, for example, run out of memory. That's the same thing for B4 and for B6. Nothing changes there. Now, there are a couple of other implications that are different when it comes to IPv6. And that basically has to do with the fact that, first, the identification field is not part of the mandatory IPv6 header, and the other one has to do with the length of the identification field. So one of the attacks that was possible with IPv4 fragmentation is that you could basically trash all the IP ID space. So if the attacker went to send forged fragments with, of course, spoofed IPv4 addresses. He could trash the whole IP-ID space, so fragmentation between a couple of systems would not work, because when legitimate fragments were received by that system, they would be reassembled with the forged fragments that the attacker had sent. Well, in this case, the IP-ID collisions are much less likely, basically because of the larger IP-ID space. Here we have a 32-bit compared to the 16-bit field that we had in IPv4. Then another of the implications is that in IPv6, the identification field is not mandatory. So if you think about some of the possible ways to exploit the IP-ID field, for example, the dump scan, that is currently implemented in Nmap, but was originally introduced in the hping tool. That tool took advantage of predictable IP-ID values, so that, for example, you could exploit the IP-ID field to perform a very stealth network scan. When in this case, as the IP-ID field is not mandatory, it's not that easy to exploit the field in that way. And finally, something that has recently changed with IPv6 fragmentation is that you know that in IPv4, fragments are allowed to overlap, which means that you can have a fragment and then receive another fragment that overlaps with the previous fragment that you got. In the past, that was used to bypass firewall rules, because basically you send a first fragment that contained source destination addresses and source and destination ports that were allowed by the firewall, and then you send another packet after that one that would overlap with the first fragment. So you would end up overriding the source and destination port, and you at that point you had bypassed the firewall rules. Well, I think it was last year or a couple of years ago, the IETF published RFC 5722, which basically forbade the use of overlapping fragments in IPv6. Actually, I don't really know why they were actually allowed in the first place, but they ended up deprecating that of having overlapping fragments. But if you really think about if that buys you anything, in my opinion, that doesn't buy you much. You could, for example, I still have to build some tools to try that, but it would be possible to, for example, intentionally cause the destination system to discard some overlapping fragments and still be able to bypass firewall rules. If you want more specific details when we get to the question section, I can provide further details. So for the most part, the security implications between IPv4 and IPv6 fragmentations are the same. So, for some of these issues that I'm discussing in this presentation, I have tried to provide or list some switches that you have in BSD systems to tune some parameters. For example, in this case, those that have to do with fragmentation and reassembly. The two ones that I'm mentioning here is limits that can be enforced on the number of maximum fragmented packets and on the maximum number of fragments. If you think about it, this is something that should probably be applied to almost anything that you do in the network code. Whenever there's something that can grow and that an attacker could make grow without any bounds, well, of course, that can be exploited to exhaust system memory. Here I'm not providing any details about some cases in which some systems should be performing these checks and they don't. We have found a couple of mechanisms that you can actually exploit to basically exhaust the whole system memory, just because they don't enforce any limits on the memory that they allocate. For example, in this case, it could be for fragment reassembly. So these are the two control switches that you have. The first one, the max frag packets, enforces a limit on the maximum number of fragmented packets that you have, and the second one enforces a limit on the maximum number of fragments that you have. I'm mentioning the defaults here in these slides for OpenBSD and FreeBSD because those are the ones that I was checking while I was working on the slides, but the numbers shouldn't differ that much if you jump to NetBSD or some other system. Okay, let's discuss ICMP version 6 then. Well, here is a very brief overview of what ICMP version 6 is used for in the IPv6 protocol suite. First of all, it's used for fault isolation. Fault isolation is basically that of being able to report network problems. Think about ICMP unreachable messages and so on. Second one is troubleshooting, for example, ping. Then ICMPv6 is used for address resolution, which means that when you need to map an IPv6 address to the corresponding link layer address, in the case of IPv6, that mapping is performed with ICMP version 6 instead of the address resolution protocol. And finally, it's used for stateless address auto-configuration, which means that you don't, strictly speaking, you don't need DHCP version 6 for IPv6 node to be able to auto-configure themselves. So one key difference between version 6 of ICMP and version 4, if you want to call it, is that in the case of ICMP version 6, it is mandatory. It's used for address resolution, so if you don't actually support ICMP version 6, you cannot map an IPv6 address into the corresponding link layer address, so basically you cannot make two systems communicate with each other. So one of the first functions that I was mentioning about ICMP was that of fault isolation. Here I'm providing a list of some of the error messages that are specified in RFC 4443. That is the latest revision of the ICMPv6 specification. As you may see from destination unreachable, packet to big, that's the IPv6 version of fragmentation needed by the F-bit set, and the other messages, they sort of parallel the same error messages that you have for IPv4, so it's sort of the same thing. Okay. So what could go wrong with ICMP version 6 messages? Well, this is, I think it was in 2004 or 5, I have made a presentation on well-known security implications of ICMP before that were still affecting some implementations. Well, the problem here is that there are some implementations that not only got wrong ICMP before, but they also got wrong on IPv6. So some, for example, will abort connections if an ICMPv6 message is received for that connection. This is not the case with BSDs. They don't abort connections for when an ICMPv4 message is received, and they do the same thing with ICMPv6, so nothing changes here. And one of the error messages that deserves like a specific discussion is ICMP packet too big, because this is the message that is used for parent-u discovery, and it's one of those that you really don't want to filter on the network, because that would prevent end systems from discovering the parent-u of a connection. The security implications of ICMPv6 packet too big are well known. It's the same thing as you had for the ICMPv4 fragmentation needed and the F-bit set. Basically, if an attacker is able to force a packet too big message, it could, in theory, cause the receiving system to reduce the MTU that it's using for that endpoint. One thing that changes here is that in the case of IPv6, you have a minimum IPv6 MTU of 1,280 bytes, whereas in IPv4 it was 68 bytes. So with IPv4, at least in theory, if somebody was reporting to you that the MTU was 68 bytes, well, you needed to grant that message. Whereas in IPv6, as all networks are required to have an MTU of at least 1,280 bytes, if you receive an ICMP too big that claims like a very small MTU, you don't need to reduce the MTU further than 1,280. The only thing that the specifications require is to add to your packets a fragmentation header that is used for some transition technologies that for this presentation they are out of scope. Well, in the same way as the IPv4 counterpart, there are some validation checks that should be performed on packet-to-big messages. Basically, for example, if you get one of these error messages for a TCP connection, you will get a piece of the packet that elicited that ICMP error message. That piece will contain the TCP sequence number, and you should check that. That value. And well, I provided a reference there to a draft that I had written like years ago, like 6 years ago, and it has not yet been published. It's in the RFC queue, which means that maybe in a couple of years it could eventually get published as an RFC, in which you can find like some other countermeasures that could help mitigate these issues even more than that of just checking the TCP sequence number. When it comes to controls that you have on BSD systems for the MTU thing, this is the ones that I found on OpenBSD, which don't really have to do with the advertised MTU value that you honor, but basically these two are limits that you can enforce on the system, because when you receive an ICMP packet too big, that information about the parent MTU is recorded in the routing table, so that if you don't enforce limits, this may mean that an attacker could basically make the routing table grow so much that at some point he could exhaust the memory. I have not actually tried this against other systems. I checked with FreeBSD and NetBSD, and they don't support these checks. So it's just a matter of checking whether, well, that ATA could actually be exploited. Okay. Another message that should receive some consideration is ICMPv6 redirects. Redirects were already available with IPv4. One key thing that changes here is that when it comes, for example, to redirect messages, the IPv6 specifications require that the redirect that you receive has a hop limit of 255. That's a TTL of 255. That basically means that if a node is not on the same link, it's impossible for him to actually send an ICMP message, an ICMP redirect that could be considered as valid, okay? This could change, for example, things could change if tunnels were being used, but in a native IPv6 network with no tunnels, as the hop limit is decremented every time that the packet passes through a router, the hop limit is decremented, and by the time a system receives that redirect, it won't have a TTL, a hop limit of 255. And thus the redirect will be discarded. There is a switch to actually be able to disable the use of redirects. In my opinion, I would personally turn it off. For example, in OpenBSD, it's on by default. Think about ICMP redirects as an optimization. And as nothing is going to break, I mean, there are not going to be interoperability problems because as a result of disabling them, it's safe to actually turn that feature off. It may have an impact on performance in the case that packets are not taking the best route to get to the destination system, but again, there are not going to be interoperability problems. And finally, I think this is the last ICMPv6 message that I'm discussing. There is an specification of the IETF RFC 4620 that defines node information messages. This these messages were specified as experimental, but they were included in the CAME specification of IPv6. So even when they are experimental, they are included in all the BSD variants. And as far as I was able to check, they are enabled, or at least some part of them are enabled by default in, for example, OpenBSD and FreeBSD. What can you do with these node information messages? Well, you can send a request to a node, and for example, you could ask that node to send you all the addresses that it has configured on that system, both the link local addresses, global addresses, and so on. And you can also send the same type of query with a name rather than an IP address. I think it's in the next slide. Yeah. Well, here you have the possible values that you have in the node info control that you have in all the CAME in all the CAME derived IPv6 implementations. Basically, you can have 4 different values for that variable, for that sys control. If it's set to 0, that means that the system won't answer to node information queries. If it's set to 1, it will answer to fully qualified domain name queries. If it's set to 2, it will respond to node address queries. And if it's set to 3, it will respond to all types of queries. In the case of OpenBSD, it is set to 1, which means that it will respond only to fully qualified domain name queries. And in the case of FreeBSD, it's set to 3, which means that it will answer to all queries. In my opinion, the most sensible thing to do with this is turn it off. It leaks out information that you may not be willing to give out to other systems. And in particular, these ICMP messages are not widely supported by all IPv6 implementations. So they are not actually like a method that you could use to troubleshoot your complete network, unless, of course, you are running all BSD systems in that network. I would have expected these messages to be disabled by default, but well, this is how they are. This is how they are set, at least in OpenBSD and FreeBSD. Okay. Address resolution. As I was mentioning before, address resolution in IPv6 is performed with ICMPv6 messages. This is what it's usually called neighbor discovery. Basically, every IPv6 node will have a neighbor cache. That's the same sort of thing as the ARP cache that you had on IPv4 systems. Whenever a system needs to map an IPv6 address to the corresponding link layer address, what it will do is send a neighbor solicitation on the network. And the node that has that IPv6 address will respond, of course, to that message, advertising its link layer address. Okay? So, of course, the receiving node will record that link layer address in the neighbor cache, and this is the basic mechanism by which the actual address resolution is performed. Neighbor cache in IPv6 is a little bit more complicated than the address resolution cache in IPv4, in the sense that it has reachability information, which means that for each entry that you have in the neighbor cache, each entry can be marked as reachable, stale, incomplete, and so on. Which means that it's not really that, well, I do have the link layer address for this IPv6 address and that's it, but also there is state information or reachability information about each of those entries. And every node tries to keep that reachability information up to date. Basically, if you receive notifications from an upper layer protocol, for example, you have a TCP connection with a remote node, and that system is sending you acknowledgements, well, that sort of means that that mapping is working, so you can keep that entry as reachable. Whereas if you don't get any notifications about reachability, at some point you will mark that entry as, for example, as a stale. And neighbor discovery does itself have proof packets that are used to test reachability of a specific IPv6 address in the event that, for example, you are using an upper layer protocol that doesn't actually send you any sort of feedback. So let's discuss some games that you could play with neighbor discovery. This is not, actually this is very, very different with what you have with the address resolution protocol, but while I was doing some tests with real systems, I was kind of surprised that some tests were not being, some verifications were not being made. Well, the most trivial of the attacks is the IPv6 counterpart of the address resolution cache poisoning, which means that if an attacker has access to a local network, of course he could respond to the neighbor solicitations advertising itself as the address that you're looking for, which basically means that the victim system will map the IPv6 address that it wants to communicate with to the MAC address of the attacker. This is the same sort of thing that you used to do with the address resolution protocol in IPv4. It's just the IPv6 version, okay? Now, an interesting thing is that when you advertise the MAC addresses, most systems don't really check if the MAC address that you are advertising is valid or not. For example, if you are communicating with an unicast address, well, of course, the corresponding link layer address needs to be unicast too. Well, for example, you could, it's trivial to cause a system to map a unicast address to, for example, a broadcast Ethernet address. So as an example of this, or a fun example of this, is that if you have a router, for example, that is a node that is configured to forward packets, and that router wants to forward the packet on the local network, what an attacker can do is, for example, respond to the neighbor solicitation, advertising the very same MAC address of the router as the MAC address of that IPv6 address. What will happen in that case? Well, the router will transmit the packet, will forward the packet using its sound MAC address, and as a result, he will get the packet again. So he will process the packet again, decrement the hop limit, transmit the packet to the same MAC address, receive the packet again, and so on. So this is pretty easy to check. I don't know if with the tools that are publicly available that you are allowed to do that, but you can build the tools yourself either from scratch or with other frameworks such as Capi6, and this is pretty easy to test. Just send a router, just perform a neighbor cache poisoning attack, so that you cause an IPv6 address to map to the same MAC address as that of the router, send that router a packet, and after that you will see that the router forwards the packet itself. Well, if you set the hop limit to 255, the packet loops 255 times on the router, okay? The same thing could be done. For example, you could make an IPv6 address map to a broadcast address or to a multicast address. One thing that I was thinking about was to try to produce a packet storm, but if I have, for example, two routers on a network, well, send a packet, perform a neighbor cache poisoning attack so that some IPv6 address is mapped to the broadcast address, okay? So I was trying to figure out if it was possible to make the routers broadcast the packet to themselves and then send the packet again to each other, and of course that would result in lots and lots and lots of packets. If I recall correctly, that doesn't work with broadcast Ethernet addresses, but I don't recall checking if that's possible with Ethernet multicast addresses, which could mean that if you were able to do that, you could cause a packet storm in the network. Of course, the mitigation for this is easy. The implementations of neighbor discovery should basically check that the Ethernet addresses that are advertised are legitimate. For example, they don't correspond to broadcast addresses, they don't correspond to multicast addresses, and they don't correspond to the very own system that is receiving the neighbor advertisement. One thing with these types of attacks, as opposed to the IPv4 counterpart, is that there's not that much support in layer 2 boxes to deal with these attacks, whereas in the case of IPv4, you have more support to deal with these issues. And one interesting tool that you do have is NDP-Mon, that is the same sort of tool as ARP Watch, the one that you have for the address resolution protocol in IPv4. Well, these guys produce the same sort of tool, but for IPv6, which is interesting. Okay, these are some of the controls that you have in this case in OpenBSD. I'm using OpenBSD for this slide because it's the one that has more extensive support of parameters that you can configure. One of the most interesting ones that you have here is the first of all those that sets a limit, an upper limit, on the maximum number of entries that you can have on the neighbor cache, okay? If you don't enforce such a limit, of course you can actually make the neighbor cache grow as much as you want, and the results are obvious, okay? One thing that is different between this sort of, some of the attacks that you can perform with neighbor discovery as opposed with the address resolution protocol in IPv4 is that IPv6 networks are typically much larger. If you think about a 64-bit interface ID, that means that at least in theory you could have lots and lots of systems on that network, which means that it would be pretty easy to make the neighbor cache grow as much as you want. And if you are not enforcing these sort of limits in your system, then chances are that you could have trouble. Okay, so let's jump to stateless address configuration. This is one of address auto configuration was one of the features that about which there were all these sort of marketing type claims about IPv6. Well, actually, there are lots of marketing type claims about IPv6. If you really think about this, auto-configuration was already supported with IPv4. Actually, DHCP is auto-configuration, okay? You don't have to manually configure your system to be able to access the network. But the only additional thing that IPv6 has is that other than the stateful or DHCP auto-configuration mechanism, IPv6 supports stateless auto-configuration, which means that rather than accessing, for example, a DHCP v6 server, nodes, when a node joins a network, it will send the router solicitation on that local network, and whichever router is available on that network will send a response with all the parameters that are needed to actually configure the interfaces in that system to be able to access the internet. Okay, so this is the basic auto-configuration procedure. Again, when the node first joins the network, sends a multicast, a router solicitation on the network, so that whatever routers are available, they will respond to that solicitation. The node will try to configure an address, and before actually using that address, it will check that the address is unique, okay? So that's the process that is called duplicate address detection. And once the node verifies that the address is unique, it will start using that address. Okay, here is like a flow chart for the stateless auto configuration. Again, first of all, the router solicitation is sent. You get a response. You form what is called a tentative address, which means that you are sort of trying an address to figure out if that address is unique, if you can actually use it. In the event that you find that that address is not unique, then of course that means that's a duplicate, so you should probably try a different address. And if it is, if the address is unique, you can actually configure that address, that is this area of the flowchart. In IPv6, addresses have like different types of lifetimes. For example, one of them is the valid lifetime. Of course, while the address is valid, you can actually use it to send packets to other systems. And there is another parameter that is the preferred lifetime, which means that while the address is preferred, that's the address that you are supposed to use to communicate to other systems. So at some point, an address could still be valid, but not preferred. That could be the case, for example, when you are making a transition from one address that you're using to a different address that you're going to configure. You still own that address, so that if there were ongoing communications, you can continue them. But if you are just about to start a new communication instance, well, you should use some other address that's supposed to be preferred. Other auto-configuration information that is learned from the router advertisements. Well, the router will usually advertise its link layer address. Of course, if you have learned about the default router on that network, you still need to know its link layer address. You could actually learn this information by means of neighbor discovery, sending neighbor solicitations and getting neighbor advertisements. But including that link layer address in the router advertisements is a performance improvement, so that you don't need to actually do the neighbor solicitation afterwards. Another information that router advertisements usually include is the prefix information option. This option contains, of course, prefixes, and these prefixes can be used for two different purposes. One of them is for figuring out which systems are on link. So a router could be advertising prefixes, not so that you configure an address in that prefix, but basically telling you that that prefix is on link, that if you need to send a packet to a system belonging to that prefix, you can do it directly on the network without actually having to send your packets through an intermediate router. The same option can be used for auto-configuration prefixes, which means that the router will tell you, well, okay, you can or should configure your addresses with these prefixes that I have here, so that that's the way in which, when a node is doing auto-configuration, it will build its address. He takes the prefix information from this option and then generates the interface ID, for example, from the MAC address. You have a route information option, which allows routers to send more specific routes. So far, without this option, a router can only tell you, well, this is the default router, and that's it. But with the route information option, it can give you more specific routes. Okay, if you want to get to this place, you may try this other router that is on the network. The route information option also allows you to have different preferences for different routes. Then you have the MTU option that allows a router to advertise an MTU that should be used for that network segment. That could be, for example, helpful if you know that, for example, you have an Ethernet network, but you know that using the MTU of 1500 is going to cause trouble with tunnels, then a router could, for example, advertise a smaller MTU so that all the nodes in the network don't run into that trouble. And finally, you have the recursive DNS server option, which basically advertises a caching DNS server. It's one thing that is interesting is that the recursive DNS server option was only introduced a few years ago. So if you think about it, this stateless configuration thing, I don't know to what extent it was useful for. Because if you could actually configure an IP address, but you didn't have the information about a DNS server, well, I don't know what you were going to use your IPv6 address for. So few years later, or a few years ago, they ended up defining this option so that you can actually, a node can actually learn all the information that it needs with stateless auto-configuration. Before this address was specified, if you wanted to get information about a caching DNS server, you needed to fall back to DHCP so that you at least were able to learn that information. Well, some games that can be played with auto-configuration, well, there's lots. For example, a node could forge a router advertisement and advertise himself as the default router. So as a result, he would get all the packets that need to be sent out to the internet. The attacker would get those packets. The attacker could also advertise prefixes as being on link. For example, I could advertise the IPv6 prefix for Google and say that it's on link, so that the system will try, the victim system will try to contact Google on the local network. You could, for example, introduce more specific routes, which means that even if a system has the right default router configured, I could introduce more specific routes, so that actually in practice the default router is never used. You could also, for example, or the attacker could forge recursive DNS server options, which means that he could advertise himself as a DNS server, so all the DNS requests would go to the attacker. And there are quite a lot of other things that you can do. Among others, it's easy to check whether a system enforces limits on various data structures that a system needs to maintain. For example, one potential vulnerability that a system could have is that if it doesn't enforce a limit on the number of IPv6 addresses that it configures, if I am an attacker, I could advertise lots and lots and lots of prefixes for auto-configuration, so that system could end up having like 1,000 IPv6 addresses. And of course, if you make that grow without bounds, at some point the system is going to crash. Another attack that could be performed is that I was mentioning before that as part of the stateless address auto-configuration, at some point the node has to check whether the address that it's selected is unique or not. Well, the attacker could get into that game, and whenever a node that is checking whether an address is unique or not, the attacker could say, well, you know, I do have that address, so try some other address. And whenever the victim tries a different address, the attacker again says the same thing. Well, I own that address, try a different one. So with this sort of attack, you could basically cause a system to not be able to configure an IPv6 address. Some of these attacks have been implemented in the Hacker's Choice IPv6 attack suite. Also, this set of tools implement, I would say, the most basic attacks, but they don't have much support, for example, for the different router advertisement options. For example, they don't have support for recursive DNS server option, prefix information option, and so on. We did produce a set of tools for everything that has to do with neighbor discovery. We have sent those tools to vendors, and I guess that at some point we will be able to release them publicly, but it will take us some time before we can actually do that. Some configuration options that you have again, here I'm referring to OpenBSD. First one is to be able to turn the processing of router advertisements off. So you have a system-wide flag that you can use for that. In OpenBSD, it's enabled by default. Off the top of my head, I think that there was some other, I don't know if it was NetBSD or FreeBSD, that in which processing of router advertisements was disabled by default, but I don't recall. Then you can configure the number of proofs that are sent when you are checking whether an address is unique or not. And two other interesting things that you can configure in OpenBSD is that you can enforce a limit, for example, on the maximum number of IPv6 addresses that a system will configure, and the maximum number of default routers that system will configure. So, for example, with the max if prefixes, which defaults to 16, you do know that the system won't be able to configure more than 16 addresses, which of course is more than enough. If you don't enforce that limit, which I don't know if all systems do, an attacker could potentially advertise lots and lots of prefixes, and the victim system would end up configure lots and lots of IPv6 addresses. Then a couple of comments about privacy and auto-configuration and privacy. As I was mentioning before, the interface ID of an auto-configured address is, yeah.
I had a question about the previous slide.
Yeah.
Have you seen any practical, or been able to execute any practical attacks where an attacker was able to fill the number of interfaces before the correct router was able to put in the bare minimum that it needed?
Well, I tried those with BSD variants, and I wasn't able to. I mean, even if they, I don't know if all support these specific switches, but even if they don't, I wasn't able to crash them.
No, but you could cause a denial of service so that that machine is simply unable to talk to the correct router because the 16 prefixes were already installed.
Yeah. Well, that's an attack that you can perform. Yeah.
Were you able to?
Yeah. This, for the most part, these two limits that you have here is so that you don't overflow the data structures that you have for the number of IPv6 addresses that you have. But I mean, once those 16 addresses are configured already, well, you're not able to configure anymore. So.
But it doesn't matter whether you crash the machine or whether you just simply have a denial of service where the machine can't talk to anything.
Yeah, well, but the thing is that if you were to, let's say, just fill all those 16 addresses, and if that same node had IPv4, then at least you could communicate with it with IPv4. Whereas if you crash it, it's dead. I mean, no matter what it's doing. But that's the only thing. Well, as I was mentioning before, the interface ID part is selected from the MAC address of the node. It's not exactly the MAC address, but it's but you sort of modify a couple of bits, and in practice, it's end up being the MAC address. And as MAC addresses are unique, I mean, you have a global MAC address, and there's not going to be any other interface card with the same MAC address. There was this concern that auto-configured addresses would hurt privacy, which means that if I was accessing a number of sites and the site was able to record the interface ID that I had, that site could correlate my network traffic between the traffic that I send to one side and the traffic that I send to another. And think that even if you move to a different network where the prefix changes, the MAC address is still the same. So that even if the prefix doesn't really matter here, as long as the interface ID is auto-configured and is the same, you can actually correlate network traffic. To mitigate these issues, what's called privacy addresses were introduced. Basically, they set the interface ID to a random value, and for the most part, these addresses are short-lived. They are supposed to last for a few hours, a day, or something, but they are supposed to change frequently. Privacy addresses, they are supported in FreeBSD. They are not supported, for example, in OpenBSD. Here are some of the switches that you have for using them. Basically, in order to turn them on, you should set the first one of the switches to 1 and the last one of the switches to 1. The other two are parameters that allow you to configure for how long those addresses will last and so on. Okay, just sort of getting to the end. So some personal thoughts about IPv6 security in general. From my personal opinion, one of the things that I hate most is all the bold claims that are made around IPv6 that are not true. I mean, being somebody that works on technical stuff, I prefer people to tell me things the way they really are, rather than making claims about improved quality of service that they don't have, improved auto-configuration that they don't have, improved security that they don't have, and so on. And it reminds me that I was mentioning in one of the first few slides that IPv6 support in IPv6 is mandatory. Well, that's just words on paper, which means that even if it's made mandatory because of the specification, that doesn't mean that you can actually use it, or that doesn't actually mean that all systems are going to support it. You do have IPv4 implementations that have IPsec, even when it's not mandatory, and on the other hand, you do have IPv6 specification implementations that even when IPsec is supposed to be mandatory, they don't have an IPsec implementation. More work is needed on IPv6 resiliency. I personally don't think that the real implementations have been the target of attackers. If you look at the number of tools that you have available to perform this sort of attacks, there are not that many. And if you look at vulnerability advisories published on IPv6 implementations, there are not that many compared to the IPv4 counterpart. And it's, in my opinion, it's not because the IPv6 implementations are better, but rather that attackers have not yet focused on attacking or trying to exploit those implementations. There needs to be improved support of IPv6 in security devices. Usually whenever you find a firewall IPS or whatever, usually has more support for IPv4 than it has for IPv6. And finally, which I personally think is very, very important, if you listen to many of the proponents of IPv6, usually they provide like a recipe of a couple of paragraphs that say, well, you need to run IPv6, just type these 2 commands and you will have it running. Which, that's most of the part is the case with rears, people that are handling IPv4 addresses, and they are running out of those addresses, so they really want to push you to deploy IPv6. But from my perspective, that's basically insane, because even if you are able to enable it, and if you were not able to enable it from your own head, that means that you will have a network running IPv6 that you don't really know what it's doing. Okay? So I guess we may have time for one question, if there is. So we are running out of time. Well, if anybody is working on IPv6 code, please drop me an email, because we may have stuff to share with you. Okay? Thank you.